morning. Good early morning. I'm going to use Trent's problem off of Webassign just because it was on my mind. So these are his answers, which we went over last night, but I'm going to show you how to do this the quickest way using a combination of Microsoft Excel and Mathematica. And while you don't need to do that for this problem because you have only 3 here, you do need to know how to do this if the data becomes higher, a lot more. And for example, on the WPR, you've never had just 3 if you look at the old WPRs. And in fact, this year we're going to have you download Excel sheets. So there's value into what I'm showing you, and also it will give you the right answer, which is very, very important. As you're doing this, whenever you're using any kind of software to do something, you have to really know what that software is giving you, because if it's giving you nonsense, you should know that. You should be able to test that. Okay, so what I did is I first pulled these two columns into Microsoft Excel, so that I could start using Excel to answer some questions. So here, this is a finished book, but I'm going to show you the formulas. These 2 columns right here, A and B, contain the X values, which is the number of floors, and the height values, which is the Y values here. They're put in here. The first thing you should always calculate anytime you have data is the average. So the command for average in Microsoft Excel is average of the range of cells. So I want it to calculate the average of the data in cells B2 to B4. So I would type B2 colon B4. So the average is what we call a summary statistic because it gives us a summary of what has happened there. But it's limited in some way because the average is just one number. So I gave the example earlier that if I told you the average of a classroom test or a WPR was 70, you would think right away, well, most people did about a C. That's how you would think, that we're bunched up around the mean. I used to say this at Montclair State, well, the average was 70, and it wasn't lying, it was 70. But on the other hand, what happened at Montclair is we always had bimodal graphs of the spread of the data. That means that we had a high bunch of failures and a high bunch of good grades. So that 70 was not a true good summary of that data. That 70 was, in fact, although it was the average, it didn't reflect the fact that half the students failed and half the students passed. Now, I would tell them the average was 70 and not tell them anything more. Number one, because they'd probably freak out if I gave them any more information, and it would be confusing. But I wanted the people who failed the test to think that 70 was a good summary statistic, so that they would study harder. They would think, oh, well, everybody else did well, and I got this bad grade. I actually need to have more information to tell me if that summary statistic is good or not. So in the next column, what we have is we're computing the sum squared total. So I'm computing the distance my Y values are away from the mean. The bigger that distance is, the worse off the summary statistic is in telling me something about that data. So for example, the example I gave you where people were spread as failing the test or getting A's on the test, these numbers would be very large. So there's 2 ways to do this. You could actually take the number you got for the average, which is down here, 631.7, and go up here and subtract the actual point, which is actual point is in B2, so I'm going to put B2 in my formula, and I could actually put in here 631.7, which is the average. Hit enter, and then scroll this down. And there's no change in the number, you see that. If I have lots of data, I usually get irritated even having to remember a number I can't see on the screen. So I just look what cell it's in. Let's suppose the cell is in B5, that's where the average is sitting, and I'll put $5, telling my computer, my Excel, not to scroll that, and I'll scroll that down, and I get the same answer. So my sum squared total is 54,747.42. Let's check if Trent got it right. Yes, look at that. Look, he's got that. And notice that all this other data is going to get filled in as well. So the next step is to do the model, find the equation of the best fit line. It's not going to be that simple because lines are not going to be asked. However, I'm going to show you a trick in Mathematica to get any size of rows of data into Mathematica and have it automatically switch the model for you. It's just easier to do. So you don't have to do this. You can definitely do what you would like to do with, if you have a different instructor and they're using Excel in the solver, please go do that. You'll find that I'm a little bit of a lazy person, so I'm going to put this into Mathematica templates. Let me save it right now. 101, save your work, right? So let me save this, and I'll put this into the Dropbox under Mathematica templates, so you can look at it. It's pretty easy, actually. I'm going to call it fitting functions to data, because you could use lines too. What's nice about this is I can go change anything quickly. The hardest part of this is getting the data inside Excel. So I've given you the command up here. It's pretty easy. The command itself is pretty easy. It's nothing like what we did in block 3 or block 2, but the command is import string with a capital I and a capital S. And I have quotes here that I'm going to fill in. So I'm going to show you how I'm going to do that. I'm going to actually retype this in there. So take that command that I've placed there for you, put it in here, and see where I have the quotes? This is the absolute easiest way to do this. I experimented yesterday on this. So I'm going to highlight the data, the X and Y data, not the headers, just the data. Copy that, go into Mathematica, go put it in between those two quotes, paste it. Now it gives me this thing, just put yes, shift enter, and the data is now housed or held into Mathematica. The next thing is I'm going to use this command called nonlinear model fit. I should put nonlinear model fit command. And it's awesome because it gives you the best fit no matter what you put in here. And it will tell you that it cannot do a best fit sometimes. So that will tell you that something's wrong with what you typed here because it cannot fit the data. So the first thing they want is a line. So I'm going to change this, what I have here, a times x plus d. Remove these commands, these things here, because I only have an a and d. So nonlinear model fit data, just put the word data because I've already called the data. I'm going to put a line, which is mx plus b, but I'm going to call it ax plus d so that I can switch around these variables or these parameters. And then I just go shift enter, bang. It actually gives me the best fit line just by shifting entering. It gives me some other things too, and I'm going to show you that in a second. But let's just go back. I'm going to copy this answer that I got here, go back to Excel, and then in model predictions I'm going to paste that in. So that's my cell D2. I'm going to put an equal sign in front of it and replace the x with the x value, which is held in cell A2. Enter. And that gives me my model predictions. Now let's look at Trent's work, and you'll see that I have a perfect match to all of this. Now, model error, I'm big on this. I do separate out, again, you're getting my take on this. I separate out the model error because I want to see it. So I take the model error to be D2 minus B2. This is the actual height. These are my model predictions. D2 minus B2 gives me the error between the two. It has negative numbers in it and positive. That's okay. I just want to see it. And what that tells me is my worst error is in this one right here with x equals 48. But I just like to see that because I want to see right away if my model's unreasonable, and I kind of eyeball test it and check it. I skipped over the sum squared total. I've done that before. So to compute the sum squared total, I think I went over that. So that's the sum of C2 to C4, which were the square, the distances. So I'm actually calculating the magnitude of the actual points to the actual height, to the mean, to see what that deviation is. The higher that my SST is, the worse off the mean or the average is as a prediction. So let's go back to this. How do I compute the sum squared error? Well, I take that model error, which I just do it for myself. You don't have to do it like this. I like to see this myself. I recommend you do, because you do start to see things. Then I take the E2 squared. I square them because that's actually giving me a distance measure, and it also takes care of the negatives. And when I sum that, that gives me the sum square error. To calculate the R square, I take 1 minus the sum squared error divided by the sum squared total. Now, what's the value of doing all of this in Mathematica? I was told yesterday that many cadets end up with a negative R square. And I thought that was really weird. If you get the best fit model, I've never seen a negative R square. I've never had a student get a negative R square. And my only conclusion is using the solver tool, something screwed up and people are getting negative R square values. You will never get that with Mathematica. It's going to give you the best fit model right away, and you should not get a negative value for R square. So that's what we get. We get 0.98. I think it wanted you to round. Let me check what Trent has here. Notice that all these values, the error squared, they're all, Trent has them right. Sum squared total, and the parameters. Let's see the parameters if Trent got those right. We're actually using Trent's work as the approved solution. Let's see. The M and the B were 17.9 and minus 91.7. And we got that. There's the model prediction. 17.9 was the M and the B was minus 191.7. So perfect. All right, so let's go to the power model. You were told to use B equals 2. So back to this Mathematica worksheet. All I have to do here is I have to change few things around. I'm going to put the power in, x minus c. Look how easy this is. They told me the b was 2, so I'm going to put 2 there. And the parameters I'm solving for is a, c, and d. Shift enter. There I have it. My a is 0.525. My C is 27.5238, and my D is 423.018. So I'm going to do the same thing I did earlier. I'm copying and pasting that, and then I'm putting that into Excel. And instead of the X, I'm putting A2. I'm over here, I have to put a times symbol because it doesn't know that is space. So I have everything correct. Hit enter. Oops, I didn't put my equal sign in front. And then I have the power model predictions or estimates for those y values. And then I did the model error, and look, it rocks. I can actually see that. The error is very close to 0. That's what I would like to see in the model error. However, I do also notice that the model error is all positive. That tells me that this model is probably slightly overestimating. We could graph the two to see that. So that's why I do this model error calculation. I don't go straight to the SSE. But here's the SSE. I just take those values of model error and I square them. See the formula right here on the top? And I get that. Now the R square is calculated the same way. I take 1 minus I5, which is a sum square error, divided by C5, which is the sum square total. And I get an R square, which is really close to 1. Now, what about the predictions they asked for? They asked for 108th floor for both of your models. The linear model, what I do is I type in the linear model. I actually just copied and pasted out of this is what I did. I'll show you. You should know my lazy ways. So I went and copied that, hit enter, go over here, paste it, and instead of the x value being A2, I put 108. So I got 1741.5. The second one, I did exactly the same thing. I copied and pasted. You don't have to, you can type them in, but I want to get there as fast as possible. Instead of the A2, I put 108, and I got 3,823.2. And let's check. We have look at that, same thing. Okay, so that's how to do the last problem on number 44 using a combination of Mathematica and Excel. And I did spend about 5 hours yesterday trying to figure out the fastest path to getting this. So know that if this feels confusing to you, that you don't want to use Mathematica, then you do have to learn Solver. There's a video AI. There's a link inside the PDF to how to do this using Solver. But the key thing of what bothered me is that you need to run Solver multiple times to get the best fit. And Mathematica, it's one swift command, and I know that I'm right. My worry when I start to numerically experiment is I don't know that I got the best fit by doing it that way, but I know with Mathematica I can. It has some limitations, so I do want to warn you that if you do this way, what Mathematica is doing, it's running something in the background that's a little complicated. It's what we call a black box. It's an off-the-shelf package, and we don't know really what's in the back of that. I'm guessing that there's some kind of what we call least squares going on in the back. But so that's a limitation of using something like Solver to do this. However, I'm cool with that because, as you know, I'm a little bit of a sloppy mathematician who wants to go and get to that application of the problem right away. And that's why I went to look and hunt for something like this. Okay, if you have any questions, email me. My email is diana.thomas@usma.edu.